No, that's not true. Okay, today we're finishing, we're going to call this fluid dynamics. This is the third time fluid dynamics has been on this board. This is the third video in which that's true. Fluid dynamics, part 2. You could think this is part 11, but you're wrong. It's part 2. That's Roman numerals. Or tally marks, I guess it doesn't really matter. Fluid dynamics, part 2. Okay, so we had talked about density, which was a review. We had talked about Archimedes' principle, which is that a substance or an object immersed in a fluid will displace that same volume of fluid. And then we had also talked about buoyancy. And so remembering all those things, let's move on to something called Pascal's principle. So we had Archimedes' principle, and now we have Pascal's principle. This is named after a man called Blaise Pascal, which is a cool name. Pascal's principle. Blaise Pascal. Is it? Blaise Pascal, who lived from 1623 to 1662, a French scientist, discovered a useful property of fluids, it says. According to Pascal's principle, ready? Pressure applied to a fluid is transmitted. What up with that word? What does that mean? Yeah, transferred. It means like what? It means what? What's transmitted mean?
Goes through.
Goes through, yeah. Pressure applied to a fluid is transmitted throughout that fluid. And we take this absolutely for granted. People knew about this long before Blaise Pascal named it. But basically, I have a fluid in here. It's good that we do this class in the morning because I have a fluid in here. I have a fluid in here. Hey, let me have your water bottle. I'm going to put it on the ground. No, not that one. I want the squeezy one. Okay, check it out. Okay, I'm going to apply a pressure to this fluid. Are you very fond of this?
Yes.
I mean, this water. I'm not going to ruin the water bottle. You need the water that's in here. Okay, so I'm going to apply a pressure to the bottom of the fluid. It's going to come out the top. It's almost like magic, really, if you think about it. I'm putting pressure down here. Woo! And out the top it comes. Whoa! This is a good video. You can't even see it on the video, though. There we go. Now you can see it. Sorry about your backpack, Peyton. But hey, where did the pressure... I'm going to diagram this now. Thanks, Rhett. I might also slip and trip and die, but that's okay. I applied... Okay, so in step 1, I had... This is an excellent drawing. Here's my thumb. Here's my other fingies. Boop, boop, boop. They're that far apart. And I hadn't applied any pressure yet. And in step 2, I squeezed the thing. Squeeze. So I applied a pressure where? Yeah, inward. And the pressure was transmitted throughout the fluid. Why does it have to be a fluid?
Because it's a solid.
Yeah, okay. Think about it.
It doesn't have to be a fluid, though. It has to be acting like a fluid, like
right,
sand.
Right, but sand wouldn't work, would it? If I had sand in there, maybe if I had very fine sand and I squeezed it, it could go poof and poof some out the top, which in that case the solid would be behaving as a fluid. But if I filled that with concrete and let it set for a week, and then I tried it, would it work? No. Even if I had the strength to do that, because we're going to talk about property of fluids here in a second, but the fluid went from this level to out the top, right? So the pressure was forced that way. The force was actually in that direction, okay? Yeah, well, what would happen if this were sealed? And I keep applying pressure, what would happen? Yeah, okay, eventually it would take more and more force. If it were sealed, it would take more force to cause the pressure to change. But eventually the pressure would build up in the container and the container would rupture. This is a property of fluid that has to do with hydraulics, which is called this. Let me think of how to phrase it. Liquids are, you need to write this, incompressible. This is how hydraulics work. You know about the hydraulics around here it's in your farm implements. In parts of this country where there are fewer cows and more people, it's in their lowriders. What, Peyton? Why don't you just use a Kleenex though, actually? Anyway, liquids are compressible, which means that if I have a hydraulic, like for instance, if I have, and this is part of Pascal's principle, is if I have a hydraulic armature here, and I have this hydraulic hose hooked to it. Here's my, I don't know, a cherry picker or a bucket of some kind. And there's a farmer in it. Arby's. There's an Arby's employee in it. Anyway, so I have fluid in here. Hydraulics have to do with fluid. I have fluid in here. We would call it hydraulic fluid, but it would work with water. And if I apply pressure, even a small amount of pressure with a little lever or something over here, the fluid has to transfer that pressure, and it can move this huge, giant thing. It can make an enormous force because of the hydraulic fluid, because these liquids are incompressible. Would this work with a gas? No, gases are compressible. It would just crunch the gas. It wouldn't work at all. Although, to some extent it does. There's a whole separate discipline of engineering called pneumatics, where the same thing can happen with gases, but they have a certain amount of compression that goes on first. They do compress, and then after that they can behave as a hydraulic fluid. We call it pneumatics. But if it were solid, it wouldn't. The solid would just get smaller and smaller. Like if we had concrete in there and I had enough force in my hands to crunch it, it would just crunch. It would get smaller. The solids are compressible, so it would just crunch. Right here, actually the math that we could do with this, that we don't, but we could do, look at the diagram on page. Okay, we had a slight break for a fire drill, but let me try to remember where we are. Oh, we were looking at figure 15 on page 487, which has a diagram of, figure 15, which is on 487, has these fluid-filled containers, one which has a certain surface, or sorry, a area, and the other which has a larger cross-sectional area. And if we apply a small force to this small area, then a large force, great big F, if we apply a small force to this small area, then a large force is applied to the large area. Does that kind of make sense? Because the pressure has to be the same. Remember, pressure equals capital F divided by capital A. Have we talked about this? Let's just take a little side note, then have pressure. Okay, so P is pressure. Capital F is, as you know, force. Capital A is, as you know, area. We measure pressure in a unit called pascals, which is a Newton, the unit of force, divided by a square meter.
You're at a pretty good A, Mr. Kine.
Hayden, you don't need to be mean to me, okay? I'm trying my best.
I wasn't pointing out that A. Where's it?
Is it that fella?
Yeah.
Okay, give me a second.
I was so confused. I was like, it's really long.
There we go.
Right.
Okay, so pressure equals force divided by area. A Pascal is a tiny unit of pressure. We almost never use Pascal because it's so tiny. We usually use kilopascal, and even then, just the pressure of the atmosphere, which is significant, but the pressure of the atmosphere is about 101,000 pascals, 101 kilopascals, because this is a pretty low unit of pressure, because a Newton is a small amount of force. A Newton is about the weight of a paperclip, maybe 10 paperclips. And an area of 1 meter is, I'm trying to make it the camera. Well, this is a meter. So an area of 1 meter would be this length by this length. So that's a pretty large area for a tiny, tiny little bit of force. And so this is a small unit of pressure. So we usually use kilopascals. But anyway, because pressure is force divided by area, if we have a small force in a small area, we can have a great big force in a great big area. Kind of like the water bottle. The pressure exerted by my fingers was only in a small area, just my 5 fingertips, my 5 little fingies here. And I applied that a smallish force, and it applied a pretty large force to a larger area. That's how this works too. We apply a small little force with the lever, right? In manual hydraulics, in the olden days, like in my grandpa's 1930 tractor with the cherry picker, this would be actually your own strength. You just pull the lever, and it causes a small, relatively small. You're a tough dude, but it's a relatively small force in this small area, and it applies a larger force, enough to lift up the Arby's employee, Arby's guy. Okay, that's Pascal's principle. Do you have questions about any of that? Okay. And then we have one last principle. Let's erase this. Is that okay? Do you have everything from this? Do you have the equation for pressure? Because this is on the test. Pressure equals force divided by area. There's a joke. There's an awful joke. where Einstein and Pascal and Newton are playing hide and seek. And it's not a dirty joke, it's just not a very good joke. It's 1 degree better than Mr. Lovercheck's jokes. But Einstein and Newton and Pascal are playing hide and seek, and Einstein counts to 100 with his face up against a tree or whatever. And then he goes, and Newton is just standing there, and Einstein says, "Oh, I found you, Newton." And Newton has drawn a square meter, and he says, "No, you didn't find me. You found Newton over square meter. You found a Pascal." And then Pascal loses because of science. Just don't at me, please. Comments are disabled for this video. Okay, let's move on to the next principle. The next principle is called Bernoulli's principle. Bernoulli, Italian. So far we had Blaise Pascal, a French scientist. We had Archimedes, an ancient Greek philosopher. And now we have... The nice thing about this lavalier mic is that if I do a little dance to try and find my eraser, you can still hear me. Anyway, now we have Bernoulli's principle, which is named after, presumably an Italian, because the name Bernoulli sounds Italian to me. It's kind of pasta called Bernoulli, isn't there? No, Bertolli. Swiss? Okay, well still, Swiss. I'm sorry, Bernoulli. I'm sorry to the estate of... The estate of... No, what's his name? Daniel Bernoulli, a Swiss scientist. Well, what do you know? Bernoulli. I think even last year... That makes me feel... Thank you, Tatum, for pointing that out. It's right here in the book, isn't it? Bernoulli's principle is that the faster a fluid flows, the less pressure it exerts. The faster a fluid flows, the less pressure it exerts. A couple of the classic example of this is that of an airplane wing. And there's a misconception about how airplanes fly, but effectively the what we call I forget the aeronautic word for it, but basically the pitch of the aircraft, how upward point, I'm doing this on camera, the pitch of the aircraft, how pointed up it is, determines the amount of lift. And a lot of people think that like when the pilot points the airplane up, it's just like a horse, you're just pointing it where you want it to go. But that is not the case. You're pointing it up because the angle of attack, that's what I was looking for, the angle of attack, the greater angle of attack makes more lift. So there's a certain amount of lift. This is an airplane wing and cross section, so pretend there's an airplane over here. Anyway, so the wing and cross section generates a certain amount of lift, which is an upward force. It's greater than the downward force of gravity. That's why a plane flies. Okay? The faster a plane moves, because of Bernoulli's principle, the greater this lift force is. That's why it stays up. But also, if we change the angle of attack, this angle has a much greater, should draw it greater than force of lift, and this one would have even more. But then eventually we come to a problem where it can stall out when it gets to this point. But and this is Bernoulli's principle. The faster it moves, the more lift it generates. That's why you can't have. Well, can you have a plane that doesn't have wings? Can you have a flying object with no wings? I can think of two. What are they? It still has, yeah, something like a helicopter or a drone. But each of those is a little wing. Each of the things on the propeller is a little wing, which is generating enough lift force, all of them together, because they move a lot faster than a plane moves. Their actual rotational speed is probably something like 700 or 800 miles per hour. So that would be in a drone or a helicopter. There still are wings. Shh. What's the other way a thing can fly without generating lift? Principle. Okay, a rocket. I wasn't thinking, but yeah, a rocket can have just its own, the force of thrust. Here's a rocket. The force of thrust, just from the downward force of the gas flowing out, the Newton's third law, the gas puts the same force back up on it. So there's thrust force. And what's another way that a thing can fly? Bird uses Bernoulli principle. The wind isn't really flying. I mean, I don't know. That's just a fluid motion. What else?
A piece of cotton in the wind.
Okay, and what is that from? That's from, we talked about it yesterday. And this is the same thing as the thing I'm getting at, which is like a Zeppelin or a hot air balloon. What do those things fly from? No? What principle that we talked about yesterday causes these to have lift?
Archimedes'
No, well, actually, it is Archimedes' principle, but specifically, it's buoyancy. These rely on the buoyant force, F sub b. They have a lower density than the air around them. A bullet works on Bernoulli's principle. There's something about the rotational dynamics of a bullet that causes it to generate lift. But a bullet probably actually is somewhere between these two. It has a little bit of lift because of its rotation. Same as like a football. When you throw a football, there's rotation to it that causes it to have stability. But also, it has a thrust like the rocket does when it first is fired. But what this is the faster fluid flows, the less pressure it exerts. The other example is this boy here. It looks a lot like pea swan, but this boy here blowing on a piece of paper, because the air coming out of his mouth is generating a lower pressure because it's moving faster than the air below it, that generates lift in the paper. You can try it, I don't know. Now you can kind of see. See it start to lift? Yeah, let me try. That's because of Bernoulli's principle. So the fluid coming out of my mouth has a higher velocity, and therefore it has less pressure, and so the pressure beneath it is greater, which causes an upward force. Questions about Bernoulli's principle, Pascal's principle, or pressure? Okay, we do not have time to move on to the gas laws, so we will talk about those tomorrow. Bye.